Chuck, another explainer
Okay.
is bubbling up within me.
Ah.
Okay.
Right. Now, you sure that that's an explainer?
Or I gotta go to the bathroom. Is that what you're
Yeah,
saying?
I was going to say, what you have for lunch? Because,
Okay. So, so I was just thinking how much we take for granted about when we use the word energy, and it has profound origins. I mean, our understanding of energy has profound origins. The brilliance of Isaac Newton, who, discovered the laws of optics and gravity and motion and invented calculus, energy was not a fully developed concept in his time. And so I just want to sort of spend a few minutes offering an appreciation for a triumph of the human intellect to figure out what the hell energy is and then how to manufacture it and exploit it. I just want to spend a few minutes. This is like a public service announcement for energy out
nice.
there.
Yeah. One way to exploit it is cause someone Sleepy Joe. Low energy, very low energy.
Low energy. So, energy is not a thing, right? You can say a rock is a thing and you can point to it, or planet is a thing. And energy is not a thing. So it was delayed in our ability to understand what it was and how to think about it. So we knew some things. For example, when you had a cannon, back when cannons were like a popular tool in warfare,
Right.
there were physicists at the time who said, I have a cannonball and have this gunpowder, and the cannon is made of iron. Then I fire it, and if I keep doing this, the cannon gets hotter and hotter. Well, where's that heat coming from? So what is it? And so in the urge to turn energy into a thing, early ideas was that energy was a fluid, was a thing that could move in and out of objects. Okay. One of them, they called it phlogiston. Another one was a caloric. These were words invented to try to think about energy as a thing, and then it moves, and it's got to be somewhere, and so a hot cannon had more of this in it than a cold cannon. And so you had to start somewhere. We were crawling before we even could walk. And it wasn't until we understood molecules and atoms and that we were able to say, okay, and what role friction plays in this. We were able to say, so you can store energy in different ways. And when you store it, it's not manifesting itself. It's not saying, here I am, look, it's not really doing that. And when you're storing it, no, the object is not in motion. No, the object is not, it's not all these things that it is when it's manifesting. So let's take the simplest case, a roller coaster, okay?
Right.
Every roller coaster, the first ascent is the highest.
Yeah.
Okay? So what's going on? So there you go, and you're leaning back, and this thing cranks you up. It is endowing you with energy, potential energy, stored energy, potential gravitational energy. When you get to the top, you can calculate how, because we have formulas for this, calculate how much gravitational energy it handed you. I don't feel this energy. I don't know what you're talking about. Until I push you over that ledge.
Right.
Over the other side of that hill. Then what happens is your potential energy starts converting to mechanical energy, to kinetic energy. And it's an exact trade-off. An exact trade-off. So all that energy they gave you at the top,
Right.
okay, now is returned with you speeding up as you descend.
That is when the ham sandwich becomes actual vomit.
Okay. That's a transformation of another kind, right? And it's this trade-off, and it goes back and forth as you go up hills and down. If you go up a shorter hill than the first one, okay, you have enough energy to reach the top of that hill because you started out with way more energy than that at an even higher hill. You're going to lose some energy to friction, okay? So in other words, you can't ascend back to a hill exactly the same height that you started in, okay? Some energy will go to friction, and when you lose energy to friction, that makes heat, okay? That's the source of heat, when you lose energy. All right, so that's why the engine of your car gets hot,
Right.
okay? Not all the energy that you started with got transferred to the motion of the car. The losses went to friction, the friction heated your engine gets hot. Okay, so in a roller coaster, you're converting gravitational potential energy to kinetic energy and back and forth and back and forth and back and forth. And if they designed it right, the frictional energy that you lose, okay, you don't go up higher and higher. The hills you go over have to get lower and lower, and there's the last one, then you come in for the stop.
Right.
So they gave you the energy when you started at the top of that hill. So that's gravitational potential energy becoming kinetic energy. That's what's going on there. And like I said, if you go back up a shorter hill, you'll slow down. Because some of that kinetic energy is giving back to you, so you can have another little lump of potential energy to take the next hill that comes after that. All right, so that's easy. We've had roller coasters forever. You could have imagined them forever ago. But it's more complicated, or a little more physics involved, if you want to say, this molecule has energy. A molecule. Well, how am I going to get the energy out of the molecule? Just sitting there. Oh, well, you can, in one case, burn it. Burn the molecule, okay? Why is it that you can throw a log in the fire and the log is room temperature, you put in the fire, then the fire ignites the log and the log keeps burning? There's chemical potential energy in the molecules of the log. Where did that energy come from? Where did the log get that energy, Chuck? You tell me right now.
The log, it's from its molecules. It was storing.
Where did its molecules get their energy?
Oh, okay, let me think about this. From their atoms.
What did the log used to be?
No, it used to be a tree.
A tree. How does a tree get energy?
From the sun.
Thank you. So, the sun builds molecules that contain stored energy. So that's why wood burns, because it has stored chemical energy given to it by the sun.
Look at that.
And it's just sitting there, minding its own business. But that's why fires in homes are so deadly. Because all this potential energy stored in the molecules of organic matter, wood, if your house is made of wood, so that the whole thing burns, converting the chemical energy into thermal energy. So much of our lives is the conversion of energy of one form into another. And what happens while that's going on? So other forms of energy. There's energy in the nucleus of an atom.
Yes.
You split the nucleus and take it out. We make bombs doing that. Okay? So we turn nuclear energy into the kinetic energy of an explosion to do damage to things in warfare.
Gosh.
Okay? That's nuclear or chemical energy. Some chemicals will give you their energy not slowly, like a slowly burning log. They'll give it to you catastrophically. All right? And we call those bombs. Okay? Or a firecracker. Catastrophically. Boom! The energy goes to break apart the firecracker, goes into the sound that it makes, the shock wave, all of that. So our lives and everything we do is nothing but a ballet of the conversion of energy from one form into another. Do you know what the French word is for energy?
I do not.
Calorie.
Oh.
Okay.
Leave it to the French. Calorie.
Okay.
With the God.
So when we consume food that has calories, a one-for-one definition of calorie is energy.
But what does not have calories, of course, are cigarettes, which is why we smoke them. Because they are not fattening and they make you look so cool.
Thanks for that 1950s reference to cinema. French cinema.
I know.
So, but think about it. So you eat food that you look at the calorie content. That's how much energy it has. Okay? So then you consume it. You need energy to live, to move. Your heart beats. All this requires energy. You're getting it from the calories of the food you eat. So what happens if you consume more calories than you need? Your body says, store that. So it creates chemical potential energy in the form of fat. And it stores it away.
I'm not fat. I'm just filled with potential. What you talking about? You see this? This is potential. I am potentially Michael B. Jordan. I am potentially Michael B. Jordan. That's what the potential.
My six-pack is just beneath the potential.
It's just beneath all this potential. You don't even know what you can have.
And by the way, that conversion of your body's calories to your energy is not perfectly efficient. So what happens to that excess energy that's not converted? That's the inefficiency of your body. We're an engine of sorts. It's inefficient. So that inefficiency gets converted to heat. So your body heats up when you exercise. It's a consequence of the inefficiency of your body. But your body loves that because now it's part of your temperature regulating system. But I'm just saying, when you exercise, your body heats up. In the same way you drive a car, the car heats up. In the same way, the wheels and the tracks of a roller coaster are actually getting hot because of the inefficiencies of the conversion, because there's inefficiencies in every conversion of energy from one form to another. So the only point of this explainer is just to say, so much of what we do and how we live involves the clever conversion of energy from one form to another. Nuclear energy, chemical energy, which is molecular. We have kinetic energy, gravitational energy. All of this comes together, and our ability to exploit that in the service of civilization is one of the great triumphs of physics, especially 19th century physics, where they figured out, oh my gosh, look what we can do. Another quick one, just look at a locomotive, right? Well, what's going on there? Well, the locomotive, all right, I don't know if you remember, they'd have to fill up from water tanks every now and then. Okay, well, what does the water do? Well, a locomotive burns either coal or wood, and it heats so that's the chemical energy. It heats a vat of water, so it's got the stored chemical energy of the wood into the active thermal energy of the vibrating water molecules. They then evaporate, creating pressure for the steam to then move wheels to have the locomotive go forward. Oh my gosh. And that all started with solar energy that made the wood or the coal, that made the fire, that made the boiling water, that made the pressure that moved the wheels. All of this is a triumph of our understanding of energy.
Now, what you just said there, I can hear Exxon going, listen, guys, we're actually solar energy, okay? So, I just see it coming
Ultimately,
down. Ultimately,
it started
guys,
as solar energy.
this is solar energy, okay?
Fossil fuels started as solar energy. This is true. This is true. It reminds me, and we got to end right now. It reminds me of this bumper sticker. It says "No nukes," right? From the anti-nuke movement, and then the O in the "no" is an image of the sun. It says "No nukes."
No nukes. Okay, yeah,
okay.
exactly.
I know what they mean. They want you to do solar energy, but the sun makes its energy with nukes. All right, just like make that clear here. That's how that it started that way. So anyhow, I just thought I'd put all that out there, and so just to enhance our appreciation for what energy does for us, and how being clever has enabled us to build civilization on the exploitation of converting energy from one form into another.
Yeah, it has built civilization, and ultimately it will destroy civilization.
On that happy note, Chuck, thank you. This has been another Star Talk Explainer. This one on all forms of energy and how it can create and destroy all that we work for. Thank you, Chuck, for that happy thought. Neil deGrasse Tyson here. Keep looking up.